Hello, everyone. My name is Hussein Osman. I am a PhD candidate at Concordia University in Canada. I'm excited to present our paper titled with Seismic Performance of Cold Formed Steel in Moment-Resisting Frames. This work was conducted in collaboration with Professor Mohamed from Cairo University, Professor Mousa from Al Ain University, and Professor Sayed Fathallah from Military Technical College in Cairo. I will start with the introduction. It has been observed that the land limitation and growing population drive the increased demand for multi-story buildings. So steel is a popular choice in construction, particularly the hot rolled steel sections due to its high strength and resilience to surface conditions. However, these hot rolled steel section pose two main challenges. The first one is the environmental impact, as the steel industry accounts for roughly 8% of the global emissions. And the second challenge is the limitations in section size and shapes, which can lead to heavier structures and less efficient designs. Now, another viable alternative is called formed steel sections, which are more cost effective than the hot rolled steel sections. These sections are manufactured from thin steel sheets, typically ranging from 1 to 6 millimeters in thickness, and are formed at the room temperatures without the need for heating. These are there are like many advantages for the cold formed steel sections. For example, the lightweight, high strength comparing to steel area used, and can be used as structural and non-structural elements, low cost and friendly to the environment, and high construction speed, up to 50% faster than the wood and concrete, easy to forming, transporting, and installing, and of course, the having a wide range of shapes. Now, however, the primary challenges associated with the cold formed steel is the early local and distortional buckling, which can lead to a premature loss of the strength, and as a result, cold formed steel often does not reach the yield point and tend to fail at early stages. This prevents the formation of the plastic hinge, resulting in reduced ductility, diminished the seismic resistance, and ultimately compromising the structural integrity. So there is an essential need to develop cold formed steel sections and their connections within the moment resisting frames. This could help enable the cold formed steel sections to mimic the behavior of the hot rolled steel sections, making them suitable for multi-story buildings located in regions with high winds and seismic loads. In this paper, we focus on evaluating the performance of cold formed steel in moment resisting frames under lateral loads using finite element analysis. Specifically, we consider the frame with a 4-meter span, as you can see here. And as we all know that the lateral load induced moment at the frame joints. So we simplify the simulation by modeling only half of the frame. So this approach involves applying a point load at the tip of the cantilever, which could significantly reduce the computational time. The connection is designed with a two C-channel back-to-back linked by a through plate with 16 bolts through the web of the beam. So the objective of the paper is to develop a numerical model using finite element software with Rabokas or ANSYS and verify the finite element model under both monotonic and cyclic loads with actual tests. Then investigate the effect of changing the cold formed steel section dimensions and connection geometry on the seismic performance, and finally give a general conclusion about the seismic performance of cold formed steel sections. Numerical model and verification. The numerical model was developed using Abacus software. Initially, we used shell element with mesh size 15 millimeter by 15 millimeters for the beam, while solid element were employed for the through plate. The connections between the through plate and the column was assumed to be rigid, applying a full restraint in X, Y, and Z, preventing the translation and rotational degree of freedom, and to prevent the lateral torsional buckling. Lateral support were placed at 2 points along the beam length, and in case for the point of load application, a rigid body element where was applied to mitigate the local buckling at this location. To streamline the computational process, the 16 bolts connected the 2C channel beam and the through plate were modeled as elastic line connectors rather than full simulating each bolt individually. This approach significantly reduced the computational time, and for the material property, both beam and the through plate were assigned a bilinear material model with a yield strength of 240 megapascal. Regarding the cyclic loading, we adopted the protocol outlined by the AISC, the American Institution of Steel Construction Standard, to evaluate the performance of the connection. This protocol also provides classification criteria based on rotation capacity. The cyclic loading in the figure is represented by the number of the cycles on the horizontal axis and the corresponding rotations on the vertical axis. In our model, we converted these rotations into displacement at the end of the cantilever, where the displacement is determined by the beam length divided by the rotation. Here, the table shows the experimental test specimen from the literature that we used to validate our numerical model. These specimens, one of them will goes under cyclic loading, and the other one will be tested under the monotonic loading. The table shown here outlines the parameter used and the range of the study. We consider various dimensions of the cold formed steel C-sections, including different thicknesses, depths, flange widths, and the table also shows the corresponding dimensions of the through plates for each cross sections of the beam. Now, results and discussion. Here, at the verification step, showing a comparison between the experimental test and the numerical model for a 200 millimeter beam depth. The figure illustrates the relation between rotation on the horizontal axis and normalized moment on the vertical axis for both monotonic and cyclic loading specimen. The numerical model found to be aligned well with the experimental results, accurately capturing both the initial stiffness and the maximum strength. However, it has been observed that the beam does not reach its full plastic moment capacity, achieving only about 70% of the section maximum moment capacity. Additionally, the video showing here the early local buckling of the web and the flange under cyclic loading, demonstrating the progressive strength degradation with each cycles. Here we showing the results obtained across the full range of the parametric study, considering different cold formed steel cross-section dimensions. After analyzing the moment rotation curves for these cross-sections, we found that increasing the web slenderness ratio of the beam leads to a significant reduction in ductility and maximum strength, as you can see here. And as a direct consequence, the energy dissipation capacity of the connection can be significantly reduced, which could negatively affect the seismic performance of the connection. To address this challenge, various researchers have explored different strategies. Some have modified the C-section profile by bending the flange to enhance beam stiffness, which show to improve stiffness and partially mitigate the local buckling effects, as you can see here in the response curves. However, the most promising approach involving adding the out-of-plane stiffeners at a specific location with the beam or the connection with a certain arrangements. Our tests show that by adding 3 pair of vertical stiffeners and 2 pair of horizontal stiffeners in a certain manner, we could eliminate the strength decay of the backbone care for a specimen under cyclic loading, as you can see here in the gray line, and only flange buckling can occur, as you can see here in the videos. Additionally, the energy dissipation of the connection improved with each cycle, leading to a cumulative uh, increase of up to 65% comparing to the unstiffened specimen, leading to a more stable cyclic behavior and improve the seismic resistance. Finally, the summary and conclusion. First, local and distortional buckling is the reason behind the low moment capacity of the cold formed steel sections. Increasing the cylinderness ratio of the web and flanges of the cold formed steel beam increases the local buckling, which decreases in turn the ultimate strength and ductility of the connection. The cold formed steel beam needs stiffeners in order to delay the early web buckling and prevent strength decay to increase the energy dissipations, and according to our specimen, using stiffeners could increase the strength and energy dissipation by up to 65%. That's all for my presentation. I appreciate the opportunity to present this work, and thank you for your time and attention.